Welcome to the Explainer. So today we're going to treat college chemistry like the universe's ultimate accounting firm. Just like a financial ledger tracks every single penny moving through a business, thermodynamics tracks every single joule of energy entering or leaving a chemical system. So if you're a college chemistry student, or honestly just someone fascinated by how energy actually rules our world, you are in the perfect place. Here is our syllabus for today's lecture. First up, defining systems and boundaries. Then, tracking heat and work. Next, the first law, followed by gas expansion mechanics, enthalpy and state functions, and we'll wrap up with calorimetry. Let's just jump right in. Okay, I want to kick things off with a quote from Albert Einstein. He basically said that thermodynamics is the only physical theory of universal content that he was convinced would literally never be overthrown. I mean, wow. That really sets the high stakes for what we're learning today, right? This isn't just a chemistry unit. These are the foundational rules of modern physics. Section 1. Systems and boundaries. First things first. Just like an accountant needs a specific jurisdiction to audit, we absolutely have to define our system and our boundaries before we can accurately track any energy. You kind of have to think of the universe as being split into two distinct parts for our accounting purposes. The system is the specific part of the universe we're actually observing. Imagine a beaker of chemical reactants sitting on a law bench. That beaker's contents, that's our system. The surroundings are, well, literally everything else interacting with it. The air in the room, the bench it sits on, even you standing there observing it. Now, we actually classify our boundaries into three main types. First, you have an open system, like a regular open beaker, which exchanges both matter and energy with the room. Then, there's a closed system, like a sealed copper flask. It can't exchange matter, but heat energy can still easily pass right through those metal walls. And finally, an isolated system, kind of like a perfectly insulated thermos, exchanges neither energy nor matter. It is entirely cut off from the rest of the world. Section 2. Tracking heat and work. All right, now that we have our system defined, we need to look at the actual currency of these energy transfers. Because energy doesn't just magically appear, right? It transacts. To really get this, let's narrate the development of the first law through the eyes of early scientists. Tracing all the way back to the 1840s, J.P. Joule conducted some incredibly important adiabatic experiments. He actually proved that doing mechanical work on water, like literally churning it with paddles, or providing electrical heat, produced the exact same temperature change. This was a huge historical breakthrough. It showed us that work and heat are really just two sides of the same energy coin. And this brilliantly illustrates how internal energy can be changed in two specific ways. Think of work as a mechanical push, like an expanding gas pushing a piston in a modern car engine. Heat, on the other hand, is the transfer of energy that's driven purely by a temperature difference. It's like a hot cup of coffee warming your freezing hands, or a household radiator transferring energy into a cold room. Both of these completely change the internal energy of the system, just through different mechanisms. Section 3. The first law. So how does this all build into the ultimate rule of thermodynamic energy accounting? Well, the absolutely crucial point for your exam prep is this exact equation right here. Delta U equals Q plus W. Translation: the total change in a system's internal energy is just equal to the heat added to the system plus the work done on the system. It's exactly like checking your bank balance. If you want to know how much money is in the account, you just add the deposits and subtract the withdrawals. Same exact concept, just dealing with joules of energy instead of dollars. And this mathematical statement translates directly to the first law of thermodynamics, which you probably know famously as the law of conservation of energy. In nature, if you have a truly isolated system, and by the way, the entire universe itself is often considered one giant isolated system, its total energy remains absolutely constant. Energy simply transforms from one state to another. It is literally never created, and it's never destroyed. Section 4. Gas expansion mechanics. Let's apply this first law to a really practical, measurable scenario. Actually, this is exactly how principles of thermodynamics are used right now to optimize fuel usage in modern engines and battery technologies. We can contrast two very different ways a gas can expand. A reversible process proceeds infinitely slowly, taking tiny, infinitesimal steps, keeping the system in near equilibrium with its surroundings the whole time. It's kind of an idealization that extracts maximum work. In contrast, an irreversible process happens in rapid, finite steps, like a sudden gas expansion against a constant atmospheric pressure. Real-world engines operate irreversibly, for sure, but we study the reversible processes to understand the theoretical limits of engine performance. Now, as a special, totally exam-ready case, consider the concept of free expansion. If you open a valve and just let a gas expand into a total vacuum, the external pressure is zero. Because there is literally nothing to push against, absolutely no work is done. So W is zero. If the process is also perfectly insulated, heat, or Q, is zero. Therefore, the internal energy, it remains completely unchanged. Section 5. Enthalpy and state functions. Okay, let's open the next chapter of our ledger here. This outlines the vital tools you're going to need for your university chemistry calculations. First off, what even is a state function? Well, think of climbing a mountain. Your altitude at the very summit is a state function. It only depends on the fact that you are currently at the peak. It doesn't care whether you took the steep, grueling path or the winding, easy trail to get there. State functions in chemistry include internal energy, enthalpy, pressure, volume, and temperature. They describe the current state of the system, totally independent of its history. We also definitely need to contrast two fundamental types of properties. Let's use a quick analogy to make this stick. If you have a container of gas and you precisely divide it exactly in half, properties like mass and volume are obviously cut in half, right? Because they depend on the amount of the substance. We call them extensive properties. However, the temperature and the density of the gas in those halved containers, those remain exactly the same. Properties that are totally independent of the amount of substance are known as intensive properties. Now, let's talk about enthalpy, which we denote with an H. Because most real-world chemistry happens in open flasks under constant atmospheric pressure, not stuffed in perfectly sealed, rigid boxes. Internal energy alone just isn't enough. The system might actually do work simply by pushing the atmosphere out of the way as gases are produced. So we use enthalpy to track this heat at a constant pressure. This relationship, delta H equals delta U plus delta N GRT, is incredibly significant for reactions involving gases. It basically allows us to relate internal energy changes directly back to enthalpy changes. Section 6. Calorimetry. So we know the math, but how do researchers actually physically measure these invisible energy changes in a real laboratory setting? Well, they use calorimeters, and there are two main types you really need to know. First is a bomb calorimeter. This is a heavy, completely sealed steel container. Because the volume physically cannot change, it strictly measures internal energy, or delta U. It's often used to test the actual energy content of foods or fuels. A standard calorimeter, on the other hand, operates completely open to the atmosphere at a constant pressure. So it directly measures the enthalpy change, or delta H, of a given reaction. And the experimental steps are beautifully simple in theory. Step 1, you run the reaction and let it transfer heat to a surrounding water bath. Step 2, you meticulously measure the exact temperature rise of that water. And step 3, using the simple mathematical formula Q equals C times delta T, you calculate precisely how much energy that chemical reaction just released. Now, this whole process relies heavily on heat capacity. Water has a massively high heat capacity, meaning it essentially acts like a giant thermal sponge. It requires a whole lot of energy just to raise its temperature by even a single degree. And that makes it the absolute perfect insulating liquid for these precise experimental measurements. Just remember for your exams, molar heat capacity applies to exactly 1 mole of a substance, while specific heat applies to 1 unit of mass, like a single gram. And just as a quick rule for ideal gases, the difference between the heat capacity measured at constant pressure and the heat capacity measured at constant volume is simply equal to the universal gas constant, R. So Cp minus Cv equals R. This incredibly simple formula just elegantly ties together the thermal properties of gases. Wow, we've fully mastered the accounting of energy today. We know exactly how to define our boundaries, track heat, measure work, and use calorimetry to literally prove the first law of thermodynamics. But as we wrap up this explainer, I really want to leave you with a provocative thought. If energy is always conserved, what actually drives these chemical reactions to occur spontaneously in the first place? Well, next time, we're going to dive into the fascinating world of entropy and Gibbs free energy to find exactly that out. Thanks for learning with me today.